Good morning, everyone. Welcome to our webinar today. This is a part of Monash Energy Institute webinar series. Monash Energy Institute, as probably many of you know, is a multidisciplinary institute within Monash University, bringing top minds in energy together to accelerate the transition towards a sustainable energy future. The Institute builds on a community of over 170 researchers actively working in the broad field of energy. We will have a few more webinars coming up very soon. I believe the next one would be about ammonia roadmap that I encourage you to also register in that one. But before I start, I would like to acknowledge the people of the Kulin Nations on whose land we are gathered today. I pay my respects to the elders past and present. The webinar today will be about 1 hour. So we will have first the technical presentation for about 30 to 35 minutes, and we will have after that the time for Q&A. I encourage you to use the Q&A session that you can find at the bottom of the Zoom. So next to your chat, you can use Q&A. So instead of putting questions in chat, please put them in Q&A. That would be easier for us to go through them if you've got any questions. Additionally, make sure that during the presentation, if you've got a question and you want to actually get engaged in a conversation rather than writing, you can raise your hand and we can actually, you can liaise with the presenter directly. So today we've got the pleasure of having Dr. Alireza Soroudi presenting for us. Dr. Alireza Soroudi is an assistant professor at University College Dublin, Ireland, and an SFI-funded investigator of the 𝗗SIPP project. He's the author of the book Power System Optimization Modeling in GAMS in 2017. His research interests include optimization techniques in power system operation and planning, risk and uncertainty modeling of integrated energy systems. He received the prestigious ENRE Young Researchers Prize at the Informs. He is a senior member of IEEE and the associate editor of IET Generation, Transmission, Distribution, and IET the Smart Grid journals. Alireza, the Zoom is yours, the floor is yours. So you will have 30, 35 minutes and then we will start the Q&A session.
Thanks, Emily, for starting the session, Behrooz. And first of all, I need to thank Monash University for giving me this opportunity to share some of my experiences with you, audience. And thanks the audience for attending this session and listening to my presentation. So first of all, the title of this presentation is an optimal non-wire solution via utilizing the inverter-based DERs in distribution networks. So we will start this seminar. So first of all, before I start the technical content, I would like to give you some brief introduction of the project we are working on at University College Dublin, Ireland. It's a big project called the 𝗗SIP, Energy System Integration Partnership Program. And this specific project is a multi-institute consortium, and there are 25 academics from 13 schools across 5 institutions. And also you can see here that there are different work packages involved in this project. For example, uncertainty and flexibility modeling, supervisory data, weather forecasting, DERs, dynamic modeling, and also we are also involved in some kind of non-engineering kind of work packages like climate modeling, consumer behavior modeling, financial risks, and how we should develop these models. And also there are other work packages called, for example, proximity metering, commercial buildings, electrified heating, wastewater treatment, and water energy nexus, data centers, and gas supply. So all of these work packages are working together to find out how they can use the flexibilities that might exist in different energy sectors and how they can coordinate their actions all together. So I go forward. So the core strengths of 𝗲𝘁𝗀𝗱 are in different strands. For example, it's not only electrical engineering. Many of us in this call might be might be coming from the electrical engineering background, but this specific project is not only power system, but also the gas network, climate and weather, wastewater treatments, data centers, and so on. So if you want to have more information regarding this project, you can refer to the website. You can see at the bottom of this page, 𝗲𝘁𝗀𝗗𝗿, to find out more about what's happening right there. So first of all, before I start the technical content, I would like to talk about the non-wire solution, why these kind of solutions are essential these days. So first of all, when we want to resolve a technical problem, we need to be finding a solution which is quick, flexible, effective, and efficient. So for example, if you want to build a new line in a transmission level or distribution level, it might take few years to get the required permissions, and also the actual building of that line might take some time to happen. So in the meanwhile, the technical constraints are right there and they should be resolved in some way. And finally, when you reach to a solution, that should be publicly acceptable. It means that the people who are going to allow you to build a tower in their land yard should allow you to do that. Okay, otherwise they will do the demonstration against your actions. Or sometimes they do not collaborate with you to implement those policies that you have fully optimized and reach to an optimal solution for them. So having the public acceptance is a big thing these days. You can't easily use some specific technologies, for example, or build some specific infrastructures, new infrastructures for them. So these days, the utilities, even its transmission network operator or distribution network operator, they need to find out some solutions in a way that they can better use the existing assets in a more efficient way. So they need to find out how they can use whatever there exists in a better way. So the non-wire solution is something referred to this kind of situation. So we are not going to build a new transmission line or distribution and a feeder. So we want to find out the solution that doesn't need such action. So the Republic of Ireland, as you can see on the map, is located right there on the red dot. So it's on the west of UK. So as you can see, it's a very small country. And the population is scattered in the country, but more concentrated around Dublin, which is on the east side, and the Cork on the south, and the Galway on the west. So we need to find out some solution for the distribution network of Ireland in this project that I was involved in. Another project that I was involved was at the EirGrid, which is the transmission network operator. We wanted to find out some solution in order to answer the technical challenges that EirGrid had at that moment. So in that project, we wanted to find out is it possible to put some fax devices on some transmission lines in order to resolve the congestion in the system, and also resolve the overloading in case of contingencies in the system. So we had to, one solution was building some new lines, but the non-wire solution was trying to find out, is it possible to use some other technologies to use the existing transmission lines that are already there. So first of all, we analyzed the system and found the technical challenges on the grid, and then try to put these devices on the grid and find out how they can manage the system in a better way. So if you are interested, you can refer to the publication which is indicated on the bottom of this slide to read more about it. But the project I'm going to talk about today is the reserve project. So in this project, which was a European project and was running between 2016 and 2019, we were trying to find out the technical barriers that is stopping us from reaching to 100% renewable energies. So there were multiple work packages, as you can see on this slide. So I was involved in the work package number 3, voltage stability by design, and there were also 2 separate strands on this work package, transient phenomena and steady state voltages. And we wanted to know, is it possible to use the capabilities of distributed energy resources connected to the distribution network in order to resolve the technical challenges that might exist in the system? For example, let me give you some examples. If we do have a lot of PV in the system and the penetration level is high, what will happen? During the day when the sun is shining and the solar units are generating at their maximum capacity, we will have a lot of active power injected to the grid, okay? And there is a good chance of creating voltage problem to the grid. So the question is, how can we avoid that? So in this project, we were trying to find out if we do have multiple DERs of different technologies that might be solar, PV, and also battery or EV, or any other kind of technology like heat pump that exists in Ireland. How can we resolve the technical challenges that we might have in the system? So the solution we came with is using their inverter-based capabilities and find out an intelligent way to control the reactive power, okay? So the question is how much reactive power should be injected to the grid, or how much reactive power should be absorbed from the grid in order to resolve some objective function or optimize some objective functions. For example, voltage profile, thermal ratings of the cables, active losses, transformer loading, which is connecting the distribution network to the upstream network, and also how we can improve the asset utilization. That's the key word to many of the utilities. They want to improve how they are utilizing their existing assets. How can they make money using their existing assets without doing a new kind of investments? So the solution we proposed for this project was, as you can see in this slide, we were trying to find out some intelligent way to control the reactive power of DERs, or distributed energy resource, which is connected to the distribution grid. So we came up with a volt-var curve, as you can see here on this graph. So we found the relation between volt and voltage at the connection point, and also reactive power that it should inject to the grid or absorb from the grid. So these DERs do measure the voltage at the connection point, and then they will understand how much reactive power should they inject to the grid or not. So and based on the objective function that we specify for them. So here you can see an example of these concepts. So here you can see the PV cells that are connected to the grid, okay? So I start with figure number 1. So figure number 1 is assuming that the PV can generate any number of Q or P at the same time, which is not realistic because the thermal capacity of the inverter should be considered, as you can see. So the P and Q values should be always within that circle. Since PV is only generating active power, that's only in the positive side of the circle. And also the next graph is telling us, okay, if you use the whole capacity of your inverter, it means that if you use the whole P, then there is no space left for injecting Q. Then intentionally, you have to reduce the amount of P that you are going to inject to the grid, okay? So that dashed line, if horizontal dashed line, is telling you that concept. So you intentionally reduce the amount of P in order to be able to inject or absorb Q from the grid, okay? Or in case that you're only allowed to, for example, inject the reactive power, then this will be the case number 4. And also, if you have some limitation on the power factor that your PV is allowed to inject to the grid, then you will have extra kind of constraints. And the last graph is showing you the case that PV unit is able to absorb and also inject Q to the grid, considering all the practical constraints. So the question that you might ask here is, how can we understand how much Q we should inject to the grid? Okay, so this is the technical constraint that we have at the moment, but we need to find out some intelligent way to understand how much Q is required for that specific snapshot of the operation. So here we developed a 3-phase optimal power flow tool, and we injected the data of the network and the technology that is connected to the grid, the network topology, impedances, and then connection points of DERs and loads. And also the technology and the limitation of the inverters are fed to the model. And then we did some offline kind of simulation, different kind of scenarios that in reality we might face with them. Actually, when we say we, I mean the distribution network operator. So these data are injected to the model. And then using a linear regression, we found that graph is working for us. So when we talk about the volt-var curve, we are talking about a straight line in a very simplistic form. It can be a curve actually, but in a simple form, it can be a linear form. So we found the slope of this line, and the equation describing this line is obtained based on some objective function. So when each unit when it's connected to the grid, it will sense the voltage at the connection point, and then it will understand how much reactive power should be injected to the grid, okay? And for example, there are 2 ways of doing that. So once you obtain the volt-var curves for each individual DERs, you can send some signals to each individual from a central unit and tell everybody what to do. But you can imagine this will require a lot of communications, okay, and coordinations. But instead of that, we propose a kind of decentralized approach. So first of all, we did some offline simulation and tuned every volt-var curve individually for each DER in the system. And then each DER, by sensing the voltage at the connection point, will understand how much reactive power should inject or absorb from the grid, okay? Okay, so you might ask here that how should we is there any need for updating those volt-var curve? And another question is the slope of this curve, or the point which is cutting the axis, is dependent on what? On what parameters? Actually, it is dependent on everything. It's dependent on the network topology, on the scenarios of the demand, and also the generation of the ERs. But we already covered those scenarios of the load and generation. But if the network topology changes, then the volt-var curves are not acting in an optimal way, okay? So there are some positive points with this kind of configuration, because these do not need complicated kind of communication system, and they are robust because they will act individually. But when we are training them, we are somehow coordinating their actions together. But in reality, if any of them fails to work for any kind of technical reason, then the performance of the overall system is not as we expect. So we did the trial in Ireland for different kind of technologies like EV. This one was a battery, and this one was a heat pump, and also this one is a solar PV. And we checked the performance of the proposed solution. So I'm going to show you a video.
ESB is at the cusp of a new era, which has been driven by government, regulation and ambition to decarbonise heat and transport. In Horizon 2020 projects such as Reserve, we are presented with a unique opportunity to keep a finger on the pulse on where the systems of the future are going.
In ESB Networks, we delivered the various trial sites within the Reserve project and coordinated the end-to-end connection and implementation of the control schemes for the project. We've successfully tested the control concept in the real world using innovative new technologies including air source heat pumps, solar PV systems, domestic battery systems and Ireland's first vehicle-to-grid charger.
At UCD we have developed a control scheme which is helping how we can get support from renewable energies that are integrated to the distribution network. Each control scheme has been developed and optimized for each trial site separately.
We work with ESB Networks and other project partners to define ICT requirements, creating hardware and software solutions to integrate with the inverters, and enabled us to deploy the algorithms developed to the trial sites.
The solar panels behind me are one of a number of the Distributed Energy Resource, or DER, trials conducted as part of this project. The solar panels are connected to the network through 2 smart inverters, and in this particular trial, we're using the techniques developed in the project to mitigate the phase imbalance experienced across this 3-phase connection.
Here you can see the V2G trial site. At this site we have tested our algorithm for supporting the network when we have connected the electric vehicle to the grid.
So what we have here on site is we have a lithium-ion battery. It's storing energy from the solar PV panels on the roof of this building, but also we can charge it remotely and discharge it as needed. So we issue commands from our platform, which sits in the cloud, down to this site to optimize the operation of the system and respond to various different grid signals.
We have deep retrofitted the school. We've brought the heat load down through insulation and air tightness and ventilation improvements. But we've also installed air source heat pumps. A real innovation in this case is the heat pumps are remotely controllable to provide demand response services to the national grid. They're set up in such a way as to ramp up and down the heat load based on the demand from outside.
Cutting-edge low-voltage monitoring devices were deployed to validate the performance of the trial sites. These monitoring devices also allowed us to monitor the impact of the trial sites on the greater distribution network.
Increasing the penetration of renewable sources to the distribution network is one of the greatest difficulties we have. It was a fantastic experience to work in collaboration with so many experts across Europe while working on this project.
One of the best results of this project was that at the end we could see that our algorithm is working properly, and we could see the improvement in the network losses as well.
We can see ourselves playing a bigger role in the smart grid and developing comms and using some of the outputs from Reserve to scale up.
We have successfully trialled the control systems in the field, which will allow us to transition to 100% renewable electricity networks.
Okay, so we want to find out some robust kind of method to operate these renewable energy resources that are connected to the grid. So each DER or RES device, when it's connected to the grid, will see the grid as a equivalent Thevenin network. Okay, that V Thevenin and Z Thevenin and theta will change for each unit. So in this project, method is proposed to identify those parameters, and then each res is capable of reacting to that specific parameters. Okay, So, and these parameters are dependent on different kind of settings, like the status of other res, network topology, load model, capacitors that exist in the system, and upstream network. And also we had several options to do that. For example, in the base case, each res is connected to the grid without any voltage control actions. The second case, we provided the volt-var curves for each individual unit. The third one is the case when any of these devices goes out of service or turns off, then that will influence the performance of the remaining ones, okay? So we adaptively have to change these volt-var curves, but how? We analyze the system for n-1 contingencies, okay? So for each individual, when each individual res is out of service or is turned off, we found the optimal volt-var curve for the remaining ones. But in reality, which setting should be used when each device is sensing the grid at the connection point? It will understand that which contingency is happening, okay? That's the key part in this algorithm. So first of all, each res should understand what is the network topology at the moment, and then use the right volt-var curve for that specific snapshot of the system operation, okay? So that was the general framework we work on the reserve project. And also there are still lots of work to be done. For example, decision-making under uncertainty, when your input parameters are subject to uncertainty on availability. So there are several techniques to do that. For example, stochastic kind of modeling, fuzzy modeling, robust optimization, or information gap decision theory. Based on the availability of your data, there are some appropriate tools to deal with that situation. So, and also we need to do these kind of decision-making in an optimal way. So first of all, we need to find out what are our decision variables and what is our objective function, and then find the best solution for that. I want to briefly introduce one of the powerful tools for this purpose. When you have a problem, you need to find out, for example, how many objective functions you have, and what are the technical constraints or economic constraints for doing that. Or sometimes you do have more than one objective functions, as we did have in this project. For example, optimizing the voltage profile and also at the same time minimizing the power losses in the distribution network. And find some kind of Pareto optimal solutions for this project, saying that, okay, these solutions have two different attributes in terms of objective functions, and then instead of only one optimal solution, we'll provide a set of optimal solutions for the decision maker, and they will be able to decide what is the best for their own purpose. And finally, sometimes one of the objective functions is inside the constraints, and that will create a kind of multi-level or bi-level kind of optimization. The purpose of this slide is telling you when you want to make an optimal decision, you need to understand what is the structure of your problem, okay? So based on that structure, you need to find out some good kind of modeling tools for dealing with that. So there are some optimization tools existing. For example, MATLAB, I am sure many of you are familiar with that. The other one is GAMS, and also the Python or Julia or other kind of open source optimization tools. So in this talk, I'm going to briefly introduce GAMS, which contains different kind of components like data, variables, constraints, and model. Data is kind of information that you have about your problem. Variables or decision variables are those quantities that you don't know their values and you want to find out their optimal quantities. And the constraint is describing what is the relation between those data and also your decision variables. And the model can be, for example, linear programming, mixed integer linear programming, quadratic programming, mixed integer nonlinear programming, and so on. And GAMS will combine all these components all together and will give you the optimal values for your variables. So, for example, in this project, we needed the AC optimal power flow, the three-phase one. And you can see here that these are the, for example, the formula that describes the flow from one bus to another bus based on the impedance of the system. And also the technical constraints that should be satisfied are the nodal balance in active and reactive power, and also the thermal constraints of the cables. So by using these tools, you can easily implement what you need in your own application. So this is the book I have developed. So there are 10 chapters in this book: economic dispatch, dynamic dispatch, unit commitment, multi-period AC/DC OPF, energy system storage, observability of the system. And also there are some other topics in the transmission network operation and planning. And finally, energy system integration. For example, is there any chance that we can coordinate the actions of the gas network and electricity network altogether? Is there any chance to use the flexibilities that exist in the gas network for power system? And there are other sources that you might wish to have a look. This is the book I spoke about it. The other one is developed by Professor 𝗗𝘁𝗁𝗲. It's decision-making under uncertainty in electricity markets. And there is another paper published in 1999. It's available on IEEE, so you can have a look at it and get familiar with the concept. So, and that's it. And the slides are over, but I'm here to answer your questions if you have any. Thanks a million.
Thank you so much, Alireza, for this very interesting talk and very interesting topics. I believe we've got something around 20 minutes for Q&A. I believe we already have one question in the Q&A session. Do you see that, or do you want me to read it?
No, I can see that. Okay. So the question is, how accurate of a load model is required to achieve optimal volt-var curve or active distribution network management? Okay, this is a tricky question, and I'm sure that nobody knows the answer for it, but I will share my own experience with you. So in reality, the distribution network operator has some estimate of how the load is evolving in the system. So they usually use the ZIP model for describing the behavior of the demand in the system, but they have their knowledge about the demand is based on some statistical model that, for example, they say the inductive loads are creating for example, one part of the load model. And for example, the power electronic demand will create another part of it, okay? So depending on the uptake of the technologies by the customers in the distribution network, those components will change. But in reality, the distribution network operator doesn't have a precise knowledge about those kind of components, okay? So the more information you have about the demand, it will be more accurate in reality, okay? So for practical purposes, they will use some estimates. I'm sure those estimates are not very precise, but they are very conservative. So they build the system in a way that although those assumptions might not be very precise, but the solution they're providing should be working actually, you know? So to keep the lights on for everybody.
Okay, thank you so much. Any other questions? We've got quite a bit of time for a Q&A session, and you can either use the chat, well, preferably the Q&A session, or you could even raise your hand and ask your question verbally. Okay, we've got another question. How TERs communicate in the decentralized optimization?
Okay, so the DERs do not communicate with each other. So let me show you the relevant slide, that might be easier to explain on them. Okay, so in this slide, you can see the decentralized kind of concept. So first of all, those offline simulations are performed. So the volt-var curve for each individual DER is obtained. But during the calculation of those volt-var curves, kind of coordination between the reactions are already right there. It means that when you run your simulation, you are optimizing their actions all together. Okay, but once the simulation is done and you feed those volt-var curves to each individual DERs, then you are not going to change it. So the offline simulation is acting like a brain for those DERs. I know that in reality, they might face with some situation that might not exist in your offline simulations. But the more comprehensive is your offline simulation. When I talk about the offline simulation, you need to create the scenarios that DER might face with them. For example, the loading of the system, the amount of generation of these DERs, and so on and so on, okay? The different network topologies and so on. So there are some trade-off between these situations. For example, if you use a very kind of comprehensive offline simulation, then you will face with some computational kind of challenges. But since these are offline, that shouldn't be a big deal. But then you will create a volt-var curve that is hopefully working for every kind of situation that might happen in reality. Okay, so the short answer for your question is they are not communicating with each other. You as the planner will communicate it first in your offline phase of simulation, okay? And hopefully they will work. Okay, the next question. Is the distribution system known for the optimizer or it estimates that? Okay, so the question is, when you run the simulation for your distribution network, to be honest with you, when you talk with your distribution network operator and you will ask them regarding the data of their network, and they will provide you some numbers, okay? And those numbers are based on the estimates, some of them actually, for example, the demand of the customers. But the network parameters are usually known because they are related to the length of the cables and the type of the cables they have used in that specific feeder, for example. Okay, so some parts of the data are right there, but some parts are not. So there is always uncertainty about the parameters you are working with. That's why I put that slide of uncertainty modeling. Okay, I hope I have answered your questions. And the other question is asking, how do you view the role of open communication standards such as IEC 61850 and IEC 61968 in upscaling the implementation of decentralized volt-var management? Okay, so to be honest with you, I'm not familiar with these two IECs because these are more related to communication. But in order to answer your question, as I said, the technique we proposed doesn't need that much communication because, as I said, each device is acting individually, okay, and autonomously. It means that they are nothing is being communicated to the device. You can put those volt-var curve on a USB stick and put it on the device, okay, or in any other way. So they will sense the communication is the voltage actually. So at the connection point, they will sense the voltage, and they can easily find out, okay, they have the volt-var curve. They put the value of V on the graph, and they find out how much Q they should generate, okay? But if there is any way that we can communicate those set points to the device, for example, something has changed in the network, or some changes in the demand is happening, okay? So it will be worked definitely in a much better way. But as you said, some standards should be followed, and some costs will be associated with those improvements. Okay, so, okay. That's my answer to your question. I hope I have answered your question. How far we are to use AI or deep learning for optimization? Very good question. For example, in this project, we were working with distribution network operator in Ireland called ESB. So they had been using a device from a company in Switzerland. I can't remember the name, but Behrooz might know the name. They were in EPFL, but that's fine.
Is that Imperix?
No, no, that's not the name, but that's fine. They were no. It's yeah, if I remember the name, I will tell you. But they were using the deep learning kind of techniques. For what purpose? So the techniques they were using was very interesting. They were sensing the active and reactive power just in the transformer connecting the distribution network to the upstream network. And by just measuring those two quantities, they were trying to find out what is the combination of the demand in the distribution network. That was really interesting. With that small kind of measurement, how informative information can be extracted from those data. Or another kind of application can be by making just few measurements, okay? Is it possible to identify the network topology in the grid or not? Is it possible to identify which switches are on or off, okay? So these techniques will definitely help the system planner and operator to operate the system in a better way. So another question is, any standards that you have considered in DER communication? So as I said, the technique we use doesn't need the communication part, and I was not also directly involved in the communication part. So unfortunately, I can't answer your question, but the best way to have access to those kind of information is referring to the website reserve.com, I think. If you Google it, you can easily find it. There are lots of information regarding how this project has been implemented. And as I said, there are different work packages in this grid, in this specific project. They were trying to use the 5G in order to facilitate the implementation of different techniques for increasing the penetration of renewable energy resources in the system. Yeah, I can see. You mentioned the VQ curve get updated. Is there any predefined time interval to do this update, or based on the change on the network loading configuration? Yeah, they can decide to do that. Good question. So as I said, those volt-var curves are obtained based on some assumptions. So the assumptions are network topology and loading of the system and so on. Okay, so if something changes in the grid, okay, we have to update those curves. But when we say something changes, it doesn't mean that the loading of the system, because those loadings are already considered in the offline simulation phase. So if something big happens in the system, for example, some part of the network gets disconnected from the rest of it, for example, and the network topology changes, then we should send some signals to do the update or update the volt-var curve manually somehow, okay? Do you have economic data for this optimization? What kind of economic data you mean? Actually, we did test this technique for 5 trial sites. So to find out how effective is this kind of technique. So first of all, we avoided some kind of complicated communication system requirement. And then we realized that by implementing those techniques, we have reduced the, for example, active losses in the system, if I remember correctly, something between 5 to 10% in that specific network. You might say that this number is not a solid number for every kind of distribution network, that if you implement those techniques, which is correct, but the average amount of saving was between 5 to 10% in terms of active losses in the grid. So the bigger the network is, those savings might increase as well. And since it was a test kind of trial, the economic impacts might not be very significant. But if the number of DERs in the system increases, then we will see much more from it. And another thing is that, for example, in Europe, in 2020, we intended to reduce 20% of the greenhouse gases. And by 2030, another percentage will reduce. And in 2050, we are trying to make it 0 or very small. So in every European country, if they cannot achieve that decarbonization target, they will face with some kind of penalties, okay? So these kind of techniques will help different countries to better achieve those decarbonization targets, okay? So we can have a look at the economic impact from that point of view as well.
There's a question about slides and videos that I will answer before we wrap up the session, but if there is any other technical questions, I think.
Yeah, and also you can have your question emailed to me if you have anything specific. So I hope I will be in touch with you all the audience and the faculty members as well to discuss more about those interesting topics.
Yes, well, thank you so much, Alireza, for this fantastic presentation. I believe it was very informative and very good discussion at the end. Very much appreciated. Regarding the slides and the video, actually the recorded session will be available on Monash Energy Institute webinar page. So you can go to Monash Energy Institute website and you can find the recorded session, in addition to other seminars that we've had, webinars that we've had in the past and we will have in future. You can find the recordings there. As Alireza mentioned, any further questions can be directed to him directly by email, and you can be in contact with Alireza, and well, anybody is welcome, of course, to do so. I believe that would conclude our session today. I would love to thank Alireza again one more time. And also thanks to the audience, people who joined us from, I think, different time zones, in particular those in Europe. I would like to say good night to you. Have a very good night, and the rest of you in Australia, have a very good rest of the day. Thank you so much again.
Thank you very much.